2.6 is on limits involving infinity. So we'll look at a number of different cases. So I wrote all these up ahead of time because it turns out it was taking a while to write everything down. So take a moment and pause and write all these down, and then I'll walk through what the graphs would look like on all of these. So, and I'll just talk through them as we go. So draw in 8 different coordinate systems. And then write down, well, first we'll do the limit of f of x as x approaches a on the left with a negative equals infinity, and then the same thing on the right equals infinity, and then on the left negative infinity, on the left negative infinity, oops, that needs to be positive infinity, this will be positive, on the right negative infinity, and then we will take off the left or right. The limit of f of x as x approaches a equals infinity. Oops, didn't mean to put those lines there. As x approaches a equals infinity, and then as x approaches a equals negative infinity. So let's look at what those graphs would be, and then look at the next case, which is as x approaches infinity, that the function equals L, and negative infinity equals another L or something, a real number. Then we're going to define those. What are those? How do we define those? And then we'll look at some examples. So let's go back to the first one. So what does this mean? The limit of f of x, a function, as x approaches a is positive infinity. So we'll put basically the first 6 here are all vertical asymptotes, and we'll define that later, but basically the first 6, so 1, 2, 3, 4, 5, 6, those are all defining vertical asymptotes for the function. They're just different cases. So this one, so this would be like x equals a right here. And that function is going to approach, let's pick a nice color to make it fun here. So we're approaching a on the left, and it equals infinity. So the function could be doing whatever over here, and then eventually it's going to be going like that. So that's what we mean by approaching a on the left. And the next one, we have f of x approaching a on the right. Okay, so let's just put a, we can put a, doesn't matter where a is, I'll just change it up. Oops, that might be in the way. Let's do it over here. Okay, so suppose this is x equals a again, a vertical line. And let's say you are approaching on the left. So the function could be doing whatever over here, and then eventually going like that. And over here it could just be going off to whatever. That's what we mean by that limit. Let's do another one. Put a, we'll just keep a in the same place each case. So these next 2 cases, you're going to negative infinity. And then this one, you're left and right going to positive infinity. And this one, left and right going to negative infinity. So the different cases here will be, and let's just use all the colors just because. So you're approaching a, so it's still x equals a, and you're going to then go down like that. Right, so I'll just fill these in. You can do the rest. So this does whatever, and then eventually goes like that. This one would be going to negative infinity on the right, like that. Okay, and then the next one, they both are doing something. Okay, so on both sides. So the next one, we are on the left and right approaching infinity, like this, and on this side. Okay, and the next one, they're all both going down. So you'd be going like this to negative infinity, or approaching. Well, sometimes I'll say to infinity, but you're really not going to infinity. So just, it's kind of a vernacular. What I mean is, of course, you're just approaching infinity. All right, then so those are all vertical asymptotes, and x equals a would be that vertical asymptote. So you should have seen that before. You should have seen that in college algebra, graphing rational functions. 1 over x, you have approaching positive infinity and negative infinity as you approach 0, right? It goes basically up like this and then down. So you got those either cases. So you've seen this before, as well as the next one. This one is what we refer to as a horizontal asymptote. And so you have this horizontal line, and I'll call that y equals L. And I'll just do it the same here. And that is y equals L. That's what the function is approaching, as in this first case, you're approaching positive infinity. So as you're coming out like this, the graph approaches this line L. So the graph can be doing whatever, but eventually it approaches L. Same, and then the vice versa here, the graph could be doing whatever, but then eventually it approaches that line. And so that's what we are looking at. Okay, so this one is approaching L. So, and it can go like this and then kind of whatever, but eventually it gets close to L. And then this last one, I think I've used up all the colors. We'll come back to this one. As you're approaching negative infinity, the graph can be doing whatever, and then eventually get closer and closer to the line L. So I'll write this down later. These are the horizontal, so both of these are the horizontal asymptotes. And then all of these are the vertical. Okay, so let's define both of these, both cases. We'll do the infinity one first, of all the ones above. We're not going to go through the left and right and all that. We'll just define basically negative and positive, and then that'll be it. Okay, so let's take a look at that. Okay, so we'll do this definition here. So limit of f of x as x approaches a equals infinity. Right, so which case is that? It's this case right here. What does that mean? Right, so means that for all epsilon greater than 0, there exists, no, sorry, I messed that up. I was looking at the wrong one. Looking too far ahead or whatever. Okay, it means that for all m greater than 0, there exists a delta greater than 0, such that if 0 is less than absolute value of x minus a less than delta, that's the same as before, then f of x is greater than m. Meaning, eventually you can get greater than that value. Okay, so here's our graph that represents that statement. So basically, for any m, as long as you're close enough to the limiting value a, this is x equals a, then the function value will be greater than m. So you're squeezing in closer and closer and closer and closer and closer and closer will guarantee it doesn't matter the value of m, the function will be greater than that m. So that's what we mean by infinity, basically. So you don't, infinity is a concept. You got to put in inequalities and definitions for infinity. It doesn't really mathematically mean anything other than there's no number larger. If you pick a number that's really large, you just can always go larger. You pick +1 kind of thing. Okay. Next one. Might show you later a proof of that. I'm not going to expect anything for you to do. Let's look at the next couple definitions. So this is basically considered a vertical asymptote, VAs, or vertical asymptote. P is silent. Okay, next definition. First, we will let L be a real number. Okay, that's what it's approaching. And then we'll go ahead and do the two cases here. So number 1, the limit of f of x as x approaches infinity equals L means that for all epsilon greater than 0, there exists an m greater than 0, that's like a large number, such that x greater than m implies absolute value of f of x minus L is less than epsilon. So that means you're getting as close to that L as desired, right? So you basically come back here and you're squeezing in this way now on L. So you just go farther out. So here's your M. X is out here, x greater than m, and then you're as close as you want for any of those values. You squeeze in on that. Okay, so that's the idea. Negative infinity is kind of just flipping it. We'll go ahead and write this one up too. So limit of f of x as x approaches negative infinity equals L means that for all epsilon greater than 0, there exists an n less than 0, so going to the left, such that x less than n implies basically the function value is as close to L as you want. Implies that absolute value of f of x minus L, that basically means, remember, absolute value you might have been taught distance from. So the distance from L is as small as you want, as small as you need to be. So that's less than epsilon. Okay, so those are the definitions. So this is 2. This is what we refer to as a horizontal asymptote. So both of those, what we call are HAs, or horizontal asymptote. Okay, and the next case, and this is just continuing, actually I'll just erase that. This is continuing what we were doing, so I'll just call the next thing down here what we're looking at. So here's some examples of the ones we just did. So e to the x has a horizontal asymptote. Oops, I didn't mean to erase that. I meant to use that. There's a horizontal asymptote here. Right, so you're getting closer and closer to 0 as x approaches negative infinity. So this one you'd be able to say the limit of e to the x as x approaches negative infinity equals 0. Okay, this one, you have both cases. You could say the limit of 1 over x as x approaches 0 on the right equals infinity. The limit, what else would you say? The limit of 1 over x as x approaches 0. What about on the left? What's that going to be? So on the left is this way, and it's approaching negative infinity. You should be able to answer my questions in your mind when I'm doing some of these once I've gone through them. If you're just kind of, if it's not making sense, you need to go back. Okay, and what else can we say in this one? We can say the limit of 1 over x as x approaches infinity equals what? So you're going this way. What's the function doing? It's going to 0. Sorry, going to 0. We can also say the limit of 1 over x as x approaches negative infinity. What does that equal? So now you're going this direction. The function is approaching 0 again. So this one has horizontal and vertical asymptotes. And then using x equals a, let's change that to b just to be a little different. Okay, say that's or y equals. Suppose this is y equals b. So let's change what this would be. That depiction, that limit for this function f of x, so the limit of f of x as x approaches infinity equals, what would that be? It would be b. It's approaching b. Now, what I haven't talked about is approaching infinity. I mean, it's kind of like, yes, it does. So, like if you just take, you know, the limit of x squared as x approaches infinity, well, you know the graph just goes off to infinity. So it's infinity. So not really going to define that, but it's another case you do see. All right, so let's take, don't really want that one in there for these purposes right now. Let's delete that. Okay, so define those and those. Okay, so let's look at an example. A few examples here. All right, so let's let f of x equal 2x cubed minus 5 over 3x squared plus x plus 2. Okay, then find the limit of f of x as x approaches infinity. All right, so this is something you may have seen or talked about, but I want to show you the technique of what to do on this and for a rational function. So when you have a rational function like that, there's a kind of a certain algebraic thing that we try to do. So this is the technique that we do. So write this down. So when you see this rational function like this, right, polynomial over a polynomial, then you divide each term by the largest power of the denominator. All right, so when you take this limit, before you take the limit, that's what you do. So in this one, what's the largest power? And it has to be the denominator. And I'm not going to get into all the little details right now. Let's just kind of bust out some examples. So the largest power of the denominator is this 2. So don't do the 3, do the 2. That's really what you want to do. So when you take this limit, we say the limit, and then let's draw this in here. So then you get 2x cubed minus 5. Don't take shortcuts, write it all out. 3x squared plus x plus 2. Okay, and I extend that out. And then I'm going to say x is approaching infinity. And so what we're doing then is we want to multiply by 1 over x squared. And then 1 over x squared. That's what I mean by like divide by it. So you divide by, but you multiply by a fraction to make it easier on you. So do that product. Now don't show all these steps, otherwise it gets way too cumbersome. So you got to do this in your head, or I'm saying you should be able to, and otherwise it gets too messy. So you're going to distribute this to each term like that and like that, and reduce, and then see what you get. Make sure you're bringing along the limit as you go, otherwise it'll not be correct. So then we have, and I'm going to move this down a little bit. I don't know if I've just gotten worse because I can move stuff, or just I want it to look really nice. Probably a little bit of both. Okay, so the limit, and then we're going to bring that in. So you can see you'll still get 2x minus 5 over x squared. That's kind of why I needed more room. So it's 5 over x squared. And then this one you have 3 plus 1 over x plus 2 over x squared. All right, so when you take this limit now, oh, and I forgot to write x approaches infinity. When you take this limit, we want to see that all of these, that goes to 0, that goes to 0, and that goes to 0. So you're left with basically the limit of 2x over 3. So this is essentially equal to 2/3 times infinity, which is infinity. Okay, so that's equal to infinity. Right, so that limit approaches infinity. You can just say it like that. So, okay, let's try another one. So next example, suppose you had the limit of 3x to the 4th plus 5x minus 8 over 2x to the 4th minus 8x squared plus 2x minus 1 as x approaches infinity. Okay, so I want you to try this one. And I'll try to do this for you. So pause it, try it. Okay. So what do you multiply by then? And you can do this in your head. You don't have to show that step. Okay, so, but I will again, but you multiply by what? 1 over, and then what's the highest power? Is the 4. So x to the 4th. 1 over x to the 4th. And then you distribute that across. And what do we have? So I'm going to put it down here. So it's equal to the limit as x approaches infinity. Oops, that didn't work. And then distribute and simplify. So you get 3 plus 5 over x cubed minus 8 over x to the 4th, 2, why did I do that? You get 2 minus 8 over x squared plus 2 over x cubed, and then minus 1 over x to the 4th. So what happens to all these terms as x approaches infinity? Okay, so x is approaching infinity. What's happening to this, this, and this? Okay, and so yes, you should be saying they all go to 0. So this, let's change the color again. Okay, so this goes to 0, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. All those terms are approaching 0 as x approaches infinity. So what you're left with then is just 3 halves. Okay. All right, so let's continue. Let's do another example.